Hi, this is group number 5, and our project is about a smart campus monitoring system. So this slide is to show our team members and our contribution to our smart campus monitoring system project. Now let's talk about our project workflow. Our workflow started with sourcing and labeling images from campus, prepare and analyzing this data, perform feature engineering such as data augmentation, train our YOLO version 8 model to detect vehicles, and finally evaluate the AI model.
Hi, I'm Jaden Ho, and now I will be talking about the data sourcing for our project. So this part will mainly discuss about the process that how we obtain and how we handle the training data set as well as the testing data set for our model to train and learn. So let's talk about how we acquired our training and testing data set. So when you first receive the data, the project of this unit, we actually searched through the internet for the training data set. And finally, we found out the data set from the website called RoboFlow. The reason why we use the data set from RoboFlow is because the data set is actually coming with the annotation labels. This means we did not need to have to make carry out the step for annotations again. And originally, we are using 300 images and the labels for each car models or each classes. And we found out that it results in a bad classification results. So we suspected that data is not enough, so we carry out the data augmentations to make more images for the model to train and learn. So finally, we have 6 classes, which are Perodua, Alza, Arus, Asia, Beza, Toyota, Vios, and Car Others. So let's move on to the testing dataset. For testing dataset, we actually capture the image of cars around the Swinburne campus, and each of the image that contain cars from different brands and models. For example, like Nissan, BMW, and others. So this is to make sure that the the testing is can be good enough and to make a real life environment for the testing. And we will maintain the 5 model chosen, which are Produa Alza, Arus Asia Beza, and Toyota Vios. And the class others is added to handle those cars which are different from the 5 models. And when we taken the testing images, actually we have to duplicate into 3 sets of images and we adjust the brightness and exposure level for from the duplicated ones to ensure that our model will have different conditions of image for training. For example, like different lighting, is it during the daytime or nighttime? Yeah, so these are for the training purpose. So here we are going to explain how we annotate the testing data set. So first we use a theme editing functions, which is inside the RoboFlow website to do annotation for our testing data set. After we adjust the brightness level and exposure level of our duplicate photos in laptops or font. And firstly, we will create a class levels, which have 6 class levels, which are Produa Alza, Irus, Asia, Beza, Toyota, viewers and car others. Car others is to handle the other cars which is away from the five desired models as mentioned just now. So we will use a bounding box to square or to highlight a car, which is to separate them from other cars and into different classes. And the pictures shows that the result of our annotation done in RoboFlow, which is 300 to 323 total image. So let's have a look on the initial trial of our model training. So initially we are taking 300 images for each of the car models which are sourced from the website called RoboFlow. And after we have done the data pre-processing process for the data sets collected, and then we pass the data set to train a model. And at the end, the model actually comes out a bad result, which it cannot really classify the car models, or it classify the car models wrongly. So to make an improvement, we have added the other class to increase our training dataset, as we suspected that our training dataset is actually not big enough for the model to learn and train. So instead of using just 300 images for our each class of training dataset, we increase the best images from 300 to 550. And also we create a class called car artists, and inside that we have 2200 images and the labels inside. For the 550 images for each class, we carry out the augmentation to boost the number of images. We carry out the augmentation by having the horizontal flip, vertical flip, and horizontal and with vertical flip. So we will have extra 1650 images and the respective labels. So now every class we will have total 2200 for each. So the whole data set, the training data sets will consist of 30,200 images with their respective labels. After this, we carry out the testing for the model again. It comes out with a better and acceptable result.
Hello, my name is Yikong Chiu. Now I'll be talking about the data processing on the source data. Okay, now I'll be talking about how our data processing the workflow works. At first, it will goes on the start processing. As for now, it will goes on this start processing, and then it will goes to validate the file uploaded, and then to check on whether there is any corrupted images or labels. And then after it has finished checking, uh, if there is no corrupted or images in or labels inside the datasets, it will then it will display an amount of 550 images and labels as output. And then only then it will check for the and then we'll proceed on checking on the mismatch on the images and labels. And it should show that there is zero missing labels, images, or labels. If there is any different amount of values being outputted other than 550 images and label files or zero missing images and labels, then we have to go back to manually check on the dataset files. After checking finish, we will then proceed on checking on the label contents. Okay, for checking on the label contents, right, we will check on whether each label files the content is either empty, or and then after that we will also check on whether it fulfills the 5 elements required by the YOLO V8, which is the class ID, X center, Y center, width and height. And then for after checking the 5 elements, we will also check for the class ID whether it's within all 6 classes. Which, for example, we have for our classes right now, we have Perodua Alza, Arus, Beza, Asia, Toyota Vios, and car others. And then after that, we also check on the bounding box values that whether they are floats. And after checking their floats, we will check on whether the bounding box is being securely put onto the image, which is onto the object. If it's out of the object, that means that it's out of range, which is supposedly to be wrong. Okay, and that will be the end of how our dataset processing works. Okay, now let's talk about the exploratory data analysis on the mean brightness of our datasets. We can see that there are difference in the overexposed, underexposed, and normal exposure images in all the different datasets. And then after that, let's clarify that for all the 5 classes for Perodua Alza to Toyota Vios, there are under 550 images, and for car others there are 2,301 images. Okay, now let's talk about the what we observe here. We can see that the the pictures that are in normal exposure are around 400 images, all according to all in all 5 classes. And then for only for the car others, there is around 2,000 images at the normal range, the normal exposure. But for overexposed and underexposed, let's compare this. We can see that for all 6 classes, there is more overexposed images in our datasets than the underexposed images in our dataset. And here is why how we calculate the mean brightness for and determine on how the images was being put. And for example, right in how our procedure work in our code is that we set the settings on the pixel threshold to be 50, the low pixel threshold is 50, and the high pixel threshold as 200. Why we choose 50 and 200 is because for 50, 50 is also considered quite dark in a pixel value, and 200 because we are using grayscale. In grayscale, right, because it's within the range of 0 to 200, so 250. And then for 50 is already considered quite dark, and 200 is also considered quite bright for grayscale. And now after we convert to the color image as the format of RGB in grayscale, and then we calculate the average brightness for all the images. And then after that, we compute the ratio of the dark and bright pixels in the image, and then we store it into a, a list. And then after that, we will calculate the threshold and find the exposure statistics as well by using the IQR percentile, which is the 25th percentile and the 75th percentile of our whole bar chart. And then after that, the classification we'll be using on the both brightness and pixel intensity ratio. We will find the, as you can see from the code snippet here, the mean is below the under thresh and the low ratio is more than 0.5. And then only then when the mean is like, for example, a bar chart along this round and then it's in the middle, which is below 0.5, it will consider as underexposed, and if it's above, then it will consider overexposed, which is as long as below the 0.5 and over x 0.5. And then after that, we'll store the values into another uh, list where it will show, then will be printed out where it will show the total amount of images of underexposed, overexposed, and normal range, normal pictures. Okay, now we'll talk on why exploratory on the mean brightness is important. It is important as the images that are either too dark or too bright can affect the model accuracy. And to ensure, it also helps to ensure the balanced distribution of the brightness among all the classes. And it also improves the generalization and robustness of the model in various lighting conditions. After that, if there is, for example, for our case, we don't have any images that are unable, the bounding bosses are unable to put onto the images. So therefore, we don't really required, but it is also important that there is some cases that it can't the EDA can help cross-check the label quality by flagging the images that are either too dark or too bright, which unable to put the bounding box correctly. And then it also helps enhance the interpretability result as it can shows that if the result is being poor, the model performs very poorly. That means that the brightness of EDA can help in the lighting variation on contribute why the why the result is that poor. Okay, that will be the end on the exploratory on the mean brightness. Thank you.
My name is Paul Howard, and now I would like to talk about data preprocessing. Starting off with data balancing with augmentation. So base images of 550 files from 5 class model are chosen. Then these files are taken and undergo the augmentation for 3 types, which are horizontal flip, vertical flip, horizontal and vertical flip. So after undergoing this augmentation, there are extra files which can add up to 2200 images. The reason why the other models, images and labels does not undergo augmentation is because there are more than enough. So at the end, 2200 images and labels are taken from all 6 classes, which adds up to 13,200. With this method, the YOLO will be used for both object detection and classification. So for the classification purposes, we'll need to rewrite all the class IDs of the images labels from the different classes. So there are 6 classes in total, 5 chosen car model and another one for the others model. So this class ID will be used by YOLO for the classification. Next, we will need to rewrite the class ID of the labels according to the test data file. So the test data file has been annotated using RoboFlow, and then the order is harder to change there, so it is easier to change it in the training set. Next, the ID order will be starting from the ALSA, Arus, Asia, Beza, others, and then Toyota Vios. Next, I would like to talk about pre-processing and data organizing for YOLO-only method. So first, the original dataset and the new augmented dataset are merged together. Then, the images and labels from all 6 classes are combined into 2 folders, which are the images and labels. Then, using Python code and finding the images and labels, they undergoes the train valid split with the ratio of 80% for training and 20% for validation. After that, the .yml file is created. So the train and the validation path is written, and then the class will be mentioned as 6, and then the name of the class, which is the car ALSA, car Arus, car Asia, car Beza, car others, and car Vios. After the YOLO only method, I would like to talk about the YOLO and ResNet method, starting off with rewriting the class ID. In this case, YOLO will only need to identify the car, so there is only one class. Next, the class ID will be set as 0, and all the 13,200 files for the images and labels will be rewritten with this class ID. Now, I would like to talk about the flow of the pre-processing for this method. So firstly, the class ID of all the car labels are being rewritten as 0. Next, a copy of all the images and labels are combined into 2 folders like previously, which are the images and labels. This will be for the YOLO object identification purposes. Next, I would like to talk about how the ResNet folder arrangement should be. So the folder should be arranged in such a way, and the labels should be removed from them. So inside these subfolders, there will be images. So the reason why this is being done is because the ResNet will be using these subfolders to classify all the images. Next, so both the YOLO folders and the ResNet folders will undergo the train valid split with the same ratio as 80% for training and 20% for validation. As for the .yml file, there will only be one class, which is car.
So this is another step for the data preprocessing, which aims to find out the model color population. This is actually a step that prepares for the feature engineering, which we can use different colors, specific colors for different models of class. For example, like Mesa, we can use red, vs Asia with black color. However, the result on the right side shows that it is not useful enough and not efficient enough to use the color for the feature engineering, because we can see that the color are almost all the same and quite similar with each other. So we are not going to use the model color population in the feature engineering in this case. And for choosing the color population, we use different sample size, and from the diagram on the right side, the first one at the top is using sample size of 10, following by 100, and the last one is 300. So different size of the sample help us to know the result is actually really not useful enough, as all the result comes out similar. And in this model color population, we also use the k size equals to 3, which is to cluster the pixel color into k cluster, and the k means the number of top dominant colors for each car model. So here we will use k equals to 3, as we get the top 3 dominant colors only. And the order will be from the leftmost bar, representing the more frequent color, until the least frequent color on the right side. So here are the 5 result of 5 models with each most dominant colors, 3 dominant colors of the model.
After the pre-processing, I would like to talk about the train validation split. So by using this code, the train and validation split can be made for the YOLO only method. So firstly, the path for the source and the output is defined. Then, setting the training ratio to 80% for training and 20% for the validating. After this, there will be a 10,560 files, both images and labels, will be split to the training, and 2,640 images and labels are split to the validating. And then on my left will be the output file, which is the train, and then the val for the validating.
Hello, my name is Jack Heng Tekway, and I'll be presenting on the models training and evaluation in both validation and real-life testing. Now I'd like to start my presentation on the model training process with YOLO V8S. So I would like to begin with the training script to train the YOLO V8S model. So in this script, we have 2 main functions, which the first one is the box IOU, which is very crucial to calculate the IOU bit and the confidence between the predicted box and the ground truth box. And then the second one is the evaluation model, which is evaluate model. We use this function to evaluate the performance of the trained model. And in this project, we're using the training configuration of 30 batch size. 640 image size, 50 epochs, and we'll be doing the training using the GPU. So in the training script, the first function is the box IOU function, which will be used to calculate the overlapping area between box 1 and box 2, which is the ground truth box and the prediction box. So it will produce an output between 0 and 1, and these values will determine how well does it overlap. So if the value is 0, meaning that the boxes do not overlap, and if the value is 1, which means that these boxes are overlapping perfectly. So in the training script, the second function is known as the evaluation function, which has 4 inputs: model, test images, label directory, and output CSV. So this function begins with a prediction function, which will create the prediction boxes coordinate known as PERD, and at the same time it will load the ground truth box coordinate known as GT. So having these two coordinates together, the function will use the box IOU, GT, and PRID as the input function for the program to calculate the accuracy of the prediction result. And this is how the model will be evaluated. Now after these two functions, we will proceed with the main training process, which is in the main function. So right here we have the model training configurations, having the batch size, image size, epochs, and the GPU device. So we will use these 4 parameters to be put into the model train function, and using the data.yml file. Then from that, we'll train the model, and we will input the model and the result and the validation image into the evaluate model function that we just explained earlier on, and that will give us the result of the model. So right now we will head into the detection and classification script, which will use the pre-trained model that we just did in the training script. Then we will use this script to use real-life testing images to see whether the trained model is capable to do so or not. So in this detection.py, we have 3 main functions, which is the get latest best model, which we will use to select the trained YOLO V8S model for the real-life testing. And the second function is the collect class name, that we will just only use this just to check whether the classes we have is the same as the model. And the third one is the detect and classify, which is the main function that we will take in the image from the real life scenario. Then the model will make predictions and produce an output that we can see from that. And in this script, the testing configuration, we will take the image source from the Swindon indoor and outdoor parking, and we have the input image size of 1600. We need to choose a high resolution so that the model can accurately identify each of the pixels and make correct prediction. So in this, we have the first 2 functions, which is to get the latest best model and the get class names model. So on the left side here, here's the function that we use to select the trained model. That in this code, we select the specific path of that model that we want to use. Then we'll paste it into the path here. Then the function will automatically take the best.pt inside that folder, and it will produce an output known as best model. Then of course you can see here we can use the best model to plug it inside to the second function, which is on the right side, which is the get class name, for us to check whether the trained model is suitable for the 6 classes that we have defined earlier on. And next, we'll move into the main detection function, which is the detect and classify function. So this function has 5 inputs, which is the model, the input directory, output directory, the CSV path, as well as the confidence threshold, which we set at 0.4, because we want the model to produce valid output, and we think that the 40% confidence is a good number. And now you can see here at the beginning of the code, we have the input car images, which we will put in all of the real-life images that we want to test. Then we run this function in the input resolution of 1600. Then it will do prediction using the model.predict function. And from there, we can obtain the coordinate of the prediction box in the same format of x1, y1, x2, y2. Then we'll annotate the images based on the prediction boxes and label. Then we'll write a CSV function just for the user to have a more detailed look into the prediction result. But at the same time, we'll also create an output folder, which is known as the output card images, where we will have the annotated images inside the folder for the user to see whether the model has made correct predictions or not. After explaining the training process of the YOLO VAS model, let's move on to the model training and real-life evaluation. So let's move on to the training results matrices. So on the left side here shows both the training and validation losses, and you can see as the numbers of epochs increases during the training process, there's a incredible drastic drop of the losses value, at least for 25% or to the maximum 95% drop in both training and validation losses here. And on the right side shows the accuracy matrices, which includes precision, recall, mmap 50 and mmap 50 to 95. And you can see here all of these values have at least 98% accuracy, which we think that is a very high value. And thus, with the very low loss value and the high accuracy value, we can say that the trained YOLO VAS model has great accuracy and without overfitting. Now we also have the validation confusion matrix for us to understand how does the model perform. You can see on the confusion matrix, you can see across all of the labels, the model has excellent performance by giving out correct predictions compared to the truth label. And you can see there is very minimal classification and detection errors. The only significant ones we have seen is more on between class VIOS and class ASIA with only 12 wrong predictions, and there's only also compared to the background classification error, which is at about 10 to 20 errors between the background and the other car brands. Now that we have evaluated the model based on the training and validation result, we'll move on to the real-life evaluation. In this slide, we have the single class and the multi-class images. Now, at the top side of the image, in both these images, there's only one class inside the image. Now we can see that in both long range, which is on the left side, and the close range, close to medium range on the right side, the model can accurately give out the correct prediction with very high value of confidence at about 90 and above. And on the bottom two, which is the bottom left and the bottom right, these are the images with multiple classes of cars inside the images. You can see on the left side, the example is the Lexus with Vios, and you can see the model can accurately provide the prediction of the Lexus as car others and car Vios. Now the similar situation, you can see it's on the right side here. Now with distinguishing the Toyota Camry and the Bezza, with also quite a certain amount of confidence, except for the middle white Bezza, because of the slight error of the model itself. Now from just now's analysis, we can see that the model do have decent performance on real life testing, but there are also certain classifications errors that we've identified during the testing, which we can summarize in three main errors. The first one is the overlapping bounding boxes on a single car, which means that the model repeatedly performed predictions and analysis on one car. And on the second one, which is the wrong labeling, which you can see here in this example on the right side, the Nissan is wrongly predicted as ASIA, while on the right side, the model still managed to predict the correct label Vios. And then the third error, which is the detection inconsistency under different brightness situation, which you can see on the left side, the RCR is correctly identified, while on the right side, the Vios was not be able to detect it due to the brightness. But on the right side, when we adjust the brightness to a lower level, the model could manage to identify both cars. Now, these three errors indicated that there's a certain amount of limitations that we have on this trained model, which we believe that could be definitely improved when we train the model on a higher resolution, and we have much more data sets of different cars and much larger varieties of lighting conditions and contrast condition, which we think that these two methods can help to improve the performance of the model.
So now we talk about the AI demonstrator and user interface ideas for our project. Our group AI demonstrator overview. Our product choose to use YOLO version 8 models, and it accepts input images like JPG or PNG. It can detect different types of vehicles and display outputs images with bounding boxes on the confidence rate. Our design highlight is that it is simple for the user to upload and viewing their result, and they do not need a technical background to use our system. And our system focus on fast and reliable vehicle detection. So here's the way for the user to use our system product. Our system was created to be simple and practical for anyone to use it. Users can just upload images like JPG or PNG, and they can just select the image and it will just start the detection process. The system can automatically process the image. Once done, it will just show the result with what car it is and the confidence scores around it. After that, user can just easily save the result as images to review later. This design is easier for security guides or other staff to check what's happening on campus. So now I'm going to talk about the conclusion for our final group project. Our project shows that YOLO version 8 can successfully detect vehicles in the campus. We originally planned to combine YOLO version 8 with the resonant model to improve the classification, but due to time and technical issues, we couldn't make it to the second stage. But the YOLO version 8 itself was good enough and showed the accurate result. For the future works and improvements, we can make these systems even better by adding support for video, so it can work with live stream and live camera. We can also include object tracking to follow vehicles over time. Working back with ResNet model may be helpful to improve accuracy and give us even more useful information about the vehicles. So I think that's all from our group. Thank you.